Today, we are going to learn the basic concepts in organic chemistry. What is the center of organic chemistry? Mechanism. That is very important. All the concepts, whatever we study, it is mainly to predict the mechanism, based on mechanism to predict the product. There are several classifications for organic reactions like SN1, SN2, E1, E2, SNAR, benzene. But I classify the organic reactions into two categories based on the mechanism. The first one, the reactions that involve charges. Second one, reactions that does not involve charges. Nearly 80 to 85% of organic reactions will come under that. Remaining 15 to 20% will be the second category. Here, since they are charges, you may know they are plus and minus charges will be there, or del plus, del minus. That means you cannot find plus or minus, but there is some partial positive character. So this del refers to partial positive and partial negative character. If I say like this, you may be familiar with this. That is nucleophile and electrophile. The reactions that involve nucleophile and electrophile. Second category, you cannot find nucleophile and electrophile. Further, there are three types. First one, pericyclic. The reactions which goes through cyclic transition state and through concerted mechanism like Diels-Order, Co, 3,3 symmetric rearrangement, all those things comes under that. Second one, radical reaction. Radical formation and its addition to double bond or with some other reagent. Third one, single electron transfer mechanism. So they call it set mechanism. So all these three accounts for only 15 to 20%. So the major contribution is from this. Nearly 80 to 85% of organic reactions can be categorized under this. If you have a clear idea about nucleophile and electrophile, and if you are able to identify them in the molecule, then you are good in organic chemistry. First, let us go to nucleophile. These nucleophiles, they are electron-rich species. The meaning of nucleophile is nucleus loving. You may know nucleus, it has proton which has positive charge. So this loves positive charge. It is possible only if this nucleophile has negative charge. That's why generally we write nucleophile like this. There is minus charge or more electron density. So this prefers positive charge which is present in nucleus. Now, I am going to categorize the nucleophile into three categories. The first one, the species which has negative charge. That is the first one. If there is minus on any species, then you can say that can act as nucleophile. For example, C minus, N minus, O minus, halogen minus. All these things can act as nucleophile. Since the valency of carbon is 4, I write like this. The remaining 3 are there. Since the valency of nitrogen is 3, this is the first category. Species which has negative charge on a particular atom. The second category, it is lone pair of electron. Organic chemistry, there is lone pair of electron on nitrogen. So you can see one lone pair of electron. In oxygen, there are 2 lone pairs of electron, and halogens, there are 3 lone pairs of electron. So this is the second one. The atom which has lone pair of electron. Carbon doesn't have lone pair. So we get nitrogen, oxygen, halogen. Addition to that, if you go for the next period, you can find sulfur, phosphorus, goes like that. But the most common thing is nitrogen, oxygen, halogen. The third category is alkene, alkyne and aromatic ring. In simple, multiple bonds. So the pi bond, it is formed by the electrons present in the p orbital. They overlap to form pi bond. So basically that is electron density, electron cloud. So that is the third category. Alkene, alkyne and aromatic ring. So benzene ring, it is basically nucleophile. It has 3 double bonds. Be thorough about this. There are only 3 type of nucleophile. The first one, species which has negative charge. Species which has lone pair of electron. Third one, alkene, alkyne and benzene. And simply you can say multiple bonds. Now what about electrophile? Again there are 3 types. First one, species with positive charge. Here you go for carbocation, just the opposite of carbanion. This is carbocation. What about N plus? If there is N plus, what about that? Generally N plus and O minus, O plus will not exist. Here the students get confused with the ammonium ion and oxonium ion. Look at this. Nitrogen has positive charge, oxygen has positive charge. But it is because it has lost its lone pair of electron. But in the carbocation, the bond has been lost. A covalent bond has been lost. Because of that, we get positive charge. In this, if there is any possibility to form like this, still lone pair of electron is there, then you can say this is positive. But in this case, the N plus refers to loss of lone pair of electron. So these two are not electrophile. Don't get confused with this. Similarly, in the case of oxygen, there are two bonds, say alcohol. If this has been removed, you will get O plus. But this is not possible. The reason I will explain later. It is not possible to form this. Similarly in nitrogen. So, the case of positive charge, we have only one option, that is carbocation. The carbocation, recently they started to call carbenium ion. Not carbonium, it is carbenium ion. The second category, carbon, which is attached to more electronegative atom. So say atom with more electronegativity. So either by single bond or double bond or triple bond. If it is attached with the atom which has more electronegativity, then there is positive charge on this carbon and minus charge on this carbon. So I have mentioned del plus and del minus because it is not completely polarized. There is partial positive character for this carbon, partial negative character on that atom. For example, I can go for this carbonyl group, which is most common. This oxygen atom is more electronegative than carbon. So what it does, pulls the electron towards this. As a result, this becomes del plus. I can go for one more group, that is nitride. It is not cyanide, it is nitride. Nitrogen is more electronegative, so it pulls the electron. So what we get is del plus and del minus. Further, I will explain that. Third one, a double bond. Already I have mentioned, it is nucleophile. It has more electron density. So it is nucleophile. The third one, it is double bond. Already I have mentioned, alkene is nucleophile. But when you attach some electron withdrawing group like this, then this carbon becomes positive. So the carbon which is on the next carbon, not this one. So a carbon which is next to the electron withdrawing group will get positive charge. So I have classified the electrophile into three categories. I hope you know what is electrophile. Basically, they are electron loving. That means the electron density is very less in that. It has positive charge. There is a special type of species. They are not electrophile, not nucleophile, but they are something different. That is nothing but benzene. What about this? Is it electrophile or nucleophile? The second one, carbene. Is it electrophile or nucleophile? Similarly, nitrene. Basically, all these things are electrophile. All these species can be attacked by nucleophile. nucleophile can attack here, but after attacking, what we get is another nucleophile. So this is electrophile. After attacking, this part has become nucleophile. That is the speciality of this category. Basically, it is electrophile. It can be attacked by nucleophile. After attacking, what we get is nucleophile on this part. Then it can add with another electrophile to give like this. Similarly, when you add nucleophile to this, what we get is minus charge. Same thing. So that is why I have categorized this separately as special type. So initially they are electrophile. After attacking by nucleophile, they become nucleophile. So this is the third category, a special type. In this video, we are going to discuss on the magnitude of electrophilicity and nucleophilicity. In the earlier video, we have discussed the different types of electrophiles and nucleophiles. I have given that here. Benzene, carbene and nitrene. I mentioned they are special type of species. Then for nucleophile, I give three types. They are here: negatively charged species, atom which has lone pair of electron and multiple bonds. For electrophile, I have given another three types, that is carbocation with a positive charge. Second one, carbon which has more electronegative atom attached to that through single bond, double bond or triple bond. Third one, alkene with electron withdrawing group. In this video, we are going to learn what will be the magnitude of this electrophilicity and nucleophilicity. In other words, which species will have higher electron density or lower electron density. So that we are going to learn now. Here I have given in the decreasing order of their electron density. In other words, I can say I have given in the decreasing order of their reactivity. That means these species, benzene, carbene, nitrene, they are highly reactive. They won't exist as such in the molecule, and in fact we cannot separate them. Then we have carbanion or negatively charged species. They are also highly reactive. Then afterwards lone pair of electron, then alkene, alkyne and aromatic ring. So these things, they are not that much reactive and they exist in the molecule as such. But these negatively charged species, they will not exist. Even if they exist, they will be highly reactive. Similarly, this carbocation, it is highly reactive. We cannot separate that. But this thing, carbonyl group, nitrile, halide and imine, we can separate them. They are somewhat stable. Last one, alpha, beta unsaturated system. So I have given roughly the decreasing order of their reactivity or the decreasing order of their electron density. There are two important concepts in organic chemistry which discuss about the electronic property in the molecule. The first one is nothing but resonance. Consider three atoms like this. I have taken A, B, C. If there is a minus charge on this, There is a double bond. Afterwards, the atom C, we have minus charge. Then this may fall here, and what we get is A minus. This is called resonance. Not only minus charge, it may be positive charge also. Carbocation. Then this bond will fall here, and what we get is A plus. Remember, the arrow always should go from the nucleophilic position to electrophilic position. Another option, even if there is lone pair of electron, then also it is possible. The lone pair of electron may fall like this, and what we get is not another lone pair, it is minus charge. Since this atom has lost its lone pair, this will become plus. This plus charge refers that this atom has lost its lone pair of electron. So we get plus as well as minus here. So this is called resonance. Generally, what we draw the resonance structure will be based on this. One minus charge migrates, another one plus charge, that is fulfilled by a double bond. Third one, lone pair of electron involves in resonance. What we get is anion as well as a plus charge. Second one, it is inductive effect. In order to understand that, you should know about electronegativity. If carbon atom is attached to another carbon atom, the two electrons present in this bond is placed in the middle. If carbon is attached to hydrogen, then also the same. The two electrons are in the middle and it is shared by both atoms. But when carbon is attached with nitrogen or with oxygen or with halogen, the electron in the bond, they are not in the middle. These electrons are pulled by the nitrogen atom or oxygen atom or halogen atom, because the electronegativity of nitrogen, oxygen and halogen, they are higher than carbon. But carbon and nitrogen, they have almost similar electronegativity. So what is that electronegativity? It is nothing but the ability of an atom to pull the electron cloud towards it. It may be in the bond or it may be lone pair of electron. So it has the ability to pull that. That is called electronegativity. And this phenomenon is known as inductive effect. Generally, this electronegativity is measured on Pauling's scale. For carbon, it will be around 2.5. Nitrogen around 3. Oxygen 3.5 and fluorine it is 4. So if you see in this period, when you go from carbon to fluorine, the electronegativity increases. You may know that fluorine atom has the highest electronegativity. It is around 4. It is not exactly 4. Approximately it is 4. It increased by 0.5 when you go from carbon to this, nitrogen to oxygen, oxygen to fluorine. It increased by 0.5. Now, let us go to the nucleophile and check how the resonance and inductive effect affect the electron density on that. First, let us go to carbanion. Negatively charged species. First one, carbanion. Next, we have N minus. The carbon valency, it is 4. In that one I have removed, I have introduced minus charge. Similarly, nitrogen, the valency is 3. I have removed one valency and I have put one minus charge. Similarly, for oxygen 2, like this. Now, here we have C minus, N minus, O minus and Cl minus. The electronegativity is higher for halogen. That means the ability to pull the electron cloud towards the atom is more for fluorine. Because of that, the available electron cloud to attack the electrophile become less. In other words, the nucleophilicity decreases. Because the available electron density is very less, so it decreases the nucleophilicity. So, this is nucleophilicity increases when you go from F minus to C minus. So, carbanion has the highest nucleophilicity. Then the second one, N minus. Next, alkoxide. The last one, halides. But the electronegativity increases in this order. Second one, what about resonance? How the resonance affects the nucleophilicity? Let us go for this. I replace one of the R group with carbonyl group. Like this. Similarly, I replace one of the R group with now it is nothing but ketone. The carbanion generated from ketone. This is nothing but amide and this is nothing but acetate. Now, this minus charge can delocalize like this. Similarly, as a result, the available electron cloud on this carbon or nitrogen or oxygen become less. In other words, this carbanion is resonance stabilized. It is more stable than this one. If it is more stable, the reactivity will be very less. So compared to this one, this carbanion has lesser reactivity, lesser electron density because it delocalizes on this carbonyl group also. Further, if I replace two groups with carbonyl group, then what I get is this one. So this compound, it is called active methylene compound, which has two electron withdrawing group or two carbonyl group. So this is active methylene compound. So the anion generated from active methylene compound, and this one it is called imide. If there is one carbonyl group, then we call it amide. If there are two, we call it imide. In this case, it is not possible. What about this? Now this minus charge can involve in delocalization on two carbonyl groups. So because of that, this is more resonance stabilized than the earlier one. Similarly, in this case, it involves in resonance on both carbonyl group. So if you compare this three, the reactivity is high for carbanion. When you go for ketone, it decreases. When you go for active methylene compounds, it decreases further. The reason is it is resonance stabilized. What about the lone pairs of electron? That is the second type of nucleophile. How does it affect? First, let us consider lone pair on nitrogen, oxygen and fluorine. This has one lone pair of electron, oxygen has 2, fluorine has 3 lone pairs of electron. Which one is more nucleophilic? The electronegativity is high for halogens and low for nitrogen. That means the available electron cloud on this atom to attack the electrophile is less here and more on nitrogen. So if you see the reactivity, nitrogen is more reactive than fluorine. The reason is electronegativity. Because of electronegativity, the available electron density on that atom is less. Now let us go for a resonance. Let us consider like this. Now let us consider these two compounds. Now this lone pair of electrons can involve in resonance and it can go like this. As a result, what we get is so you can see here I have got positive charge and minus charge on this. Similarly, like this. Now, what about the nucleophilicity of this lone pair of electron? You can see clearly in this, the lone pair of electron is not available on nitrogen or oxygen. So this cannot act as nucleophile. When the lone pair of electron is in resonance, the nucleophilicity of this group has got decreased. In fact, in this system, what we call enamine, which has electron withdrawing group, this nitrogen cannot attack the electrophile because the lone pair is not on nitrogen. It involves in resonance and the electron density got decreased and the nucleophilicity is lost. Third one, multiple bonds. Let us consider this ethylene and vinyl chloride, propene. Now, which one will have higher electron density? Which one will react faster with the electrophile? I have 3 compounds. Which one will react? Which one will attack the electrophile faster? Here, this chlorine has higher electronegativity. it tries to pull the electron cloud from the alkene. So because of that, the electron density on this alkene is less than this one. In this, there is no group, no atom to pull the electron density. So compared to this, the electron cloud or electron density is less on this group, on this compound. On the other hand, this CH3 can give some electron density to the alkene. So because of that, this has higher electron density than this. So if you go for the increasing order, the first one will be this. It has the lowest electron density because of the higher electronegativity of halogen atom. Second one will be like this one because there is no group to give or to remove the electron density. Third one is this. So this is highly nucleophilic than this or this one. What about resonance? So this is based on electronegativity. Now we are going for resonance. I go for the same compound. I attach this like this, say a carbonyl group. Now this double bond involves in resonance, and what we get is, it is O minus this one. So the electron density on this has been removed. Now this position is electrophile. This position is electrophile now. So we have discussed about that in the types of electrophile. So when I attach an electron withdrawing group, the electron cloud is being removed and we get electrophile there. I go for one more category, that is methyl vinyl ether. What about this? Here we have lone pair of electrons. It involves in resonance. As a result, what we get is this one. It is just reverse of this. When I attach an electron withdrawing group, I got positive charge there, but when I introduce electron donating group, I get negative charge on this. So the electron cloud here has got increased, but here it got decreased. The order, so this will be the lowest one, this is second, and this one third. The same concept, it can be applied to aromatic ring also. I go for this. Now you can compare this part, whatever I have shown earlier. Now I just add two more double bonds. Now this is aromatic ring. So this particular portion is nothing but methyl vinyl ether, and this is methyl vinyl ketone, similar to the one whatever I have discussed. So because of the resonance, what I get is positive charge. So it increases the electron density on this atom. But in this aromatic ring, it is further in conjugation here. So what we get is another resonance structure in which the minus charge is on this carbon. So we get minus charge on this carbon as well as this. If you go further, you will get on this carbon. Basically, the electron cloud on the ortho and para position has got increased. So now this can attack the electrophile and we will get the corresponding product. So product, whatever we get, will be like this. So we get ortho product and para product. That's why we call this OMe group is ortho and para directing. The reason is the electron density on that position is very high because of resonance. What about this? This pulls the electron from here, and what happens is the electron density on this carbon got reduced. So this carbon cannot attack another electrophile because this also plus, this also plus. The attack of this is not possible. In the earlier case, there was minus charge. It attacked the electrophile easily. But now this plus and this plus cannot react. Then further I go for resonance. What happens? I get positive charge here. So again it cannot attack. So this system cannot attack the electrophile from the ortho carbon and para carbon. This carbon and this carbon is not nucleophilic. It is electrophilic in nature because of the resonance. But what about this carbon? The metacarbon. The resonance has not affected the electron density on this metacarbon. So the electron density or electron cloud on this carbon is equal to that of benzene. Because it has not been affected, it has not been touched by the electron withdrawing group. So now this can attack electrophile. So this carbon can attack electrophile to give the product. So what we get is a product like this. Since it is in the meta position, we call it this carbonyl group is meta directing. Listen carefully. In the earlier case, methoxy group increased the electron density on ortho carbon and para carbon. But in the second one, the electron withdrawing group decreases the electron density on ortho carbon and para carbon, and the meta carbon is unaffected. That attacks. The electron density on this carbon is not increased by this group. It remains unaffected. On the other hand, ortho carbon and meta carbon, in that two position, it got reduced. In the next video, let us discuss now what will be the effect of the resonance electronegatividity. First one, it is on positively charged species. The most common one, it is carbocation. One more positively charged species is H+. We can add that also. Then the second category, that is carbon atom, which is attached to another atom which has higher electronegativity than carbon via single bond, double bond or triple bond. Third category, it is alpha beta unsaturated system. Now let us discuss the effect of electronegativity on resonance on this species. First one, I go for carbocation. What will be the effect of electronegativity on this? That means there is electronegative atom like Cl or halogen, even NO. So all these atoms, they have higher electronegativity than carbon. So if we attach this, what will happen? This is the question. But is it possible to generate carbocation here? No, it is not possible. Such system will not be stable. How we generate carbocation? Say this is some group. Instead of hydrogen, I make it some group. There are 2 electrons in this bond. If both electrons goes with the group, then there will be positive charge. Because the carbon has lost its electron. If we have halogen atom or fluorine atom like this, then in that case, the fluorine atom, since it is more electronegative than carbon, it pulls the electron towards this. So there will be del plus on this carbon. Since there is a deficiency on this carbon, this will pull the electron from this bond. So what happens? The bond, the lone pair of electron on this prefers to come towards carbon, not towards the group. So because of that, we cannot generate this carbocation. It is not possible. What will be the effect of resonance on the carbocation? Already we have discussed, if there is a system like this, then this double bond migrates here to give the resonance structure like this. So if the positive charge, if it is resonance with double bond, then we will get carbocation or positive charge on 2 carbons. So the nucleophile can attack here as well as here. Let us go to the second category, that is carbon atom attached with more electronegative atom through single bond or double bond or triple bond. Not only CN, it may be C oxygen also through single bond or double bond. The third one, carbon attached with halogens. It may be fluorine, it may be chlorine, it may be bromine, and it may be iodine. Since these atoms are more electronegative, the electron in the bond is pulled towards the more electronegative atom. Because of that, there is some decrease on the electron density for this carbon. That leads to del plus on carbon and del minus on nitrogen or oxygen or halogens. Since the electronegativity increase in this order, the del plus on this carbon will be higher than the del plus here, which will be higher than this. So this is the increasing order. What will be the effect of resonance? In order to explain that, I go for this carbonyl group. Because of the higher electronegativity, there is del minus on oxygen and del plus on this carbon. Now I am going to connect this with a double bond. So the valency of this should be 4. So I take a ketone, alpha beta unsaturated ketone like this. Since there is del plus, similar to the earlier case, this bond falls here. When it falls here, the valency becomes 5. The number of bonds to this carbon, it becomes 5. But carbon valency should be only 4. Since oxygen atom is more electronegative, it takes one of this bond, and what we get is this one. So there is a plus charge on this carbon and minus charge on our oxygen. Basically it is enolate. So in fact this is the third category, whatever I have explained. This third category, it is the extension of second one. What will be the effect of resonance in the second category that results in this? Now let us go to the mechanism. When these nucleophiles attack the positively charged species, what will be the mechanism? That is we are going to see now. Let us take H plus as electrophile, and there will be some X minus also. To that I add carbanion, a negatively charged species. This carbanion attacks this, and what we get is this bond is newly formed. It has 2 electrons. That 2 electrons are present in the minus charge. So that minus charge is used to form a bond between carbon and the electrophile H plus. Basically it is nothing but acid-base reaction. Acid-base reaction is basically a reaction between electrophile and nucleophile. We give the name acid-base reaction when the electrophile is H plus. So it is a special category. When the electrophile is H plus, we give the name as acid-base reaction. Similarly, you can try like this also. What we get is so like LDA, hexamethyl diacethylamide. So all these things, this is what happening. I can go for alkoxide, which takes H plus to give this. So all these reactions basically acid-base reaction. What about carbocation? If I add carbocation, then this attacks here. So this mechanism in which a nucleophile attacks the carbocation is known as SN1 mechanism. The earlier one, it is acid-base reaction. The second one, it is SN1 mechanism. In this, a carbocation will be formed that will be attacked by nucleophile. Now, we are going for lone pair of electron which attacks the positive charge. For example, I take ammonia or say amine. This is added to carbocation. It may be even water or alcohol thiol. All these compounds, they have lone pair of electron. This lone pair of electron attacks here, and the lone pair is used to form the bond. So what we get is N. This lone pair of electron has been used to form bond with this carbon. So what we get is, and here it is H3. What about the lone pair of electron? It is lost. So what we write is plus. This plus refers to the loss of lone pair of electron. Further, some X minus negatively charged species will take this proton because of this positive charge on nitrogen tries to pull the electron towards it. So this hydrogen becomes acidic, and the negative part of this carbocation takes that proton. What we get is so this is the mechanism. When this ammonia takes the H plus, what we get is ammonium, and the negative part says Cl. So this is acid base reaction. The earlier case, all the anions can take H plus to give that, but in the second category only this ammonia can take H plus. What about alcohol? Can it take H plus? Yes, it can. Even alcohol can take H plus to give this. But further, what happens is this eliminates water molecule to give a carbocation. So that is one method for the generation of carbocation. That's why alcohol is not considered as base. Generally the students get confused between base and nucleophile. Both are same. Base and nucleophile both are same, but they get different name based on the role of it in the reaction. We call the species as base when it abstracts proton. Basically, it is a reaction between OH minus, which is nucleophile, and H plus. When this minus charge attacks the H plus positively charged species electrophile, that is called, during that time this OH minus is called as base. The same OH minus, if it attacks carbocation, that time we call it nucleophile. The third category, I would like to explain the addition of alkene to carbocation. What happens? So already mentioned, this is nucleophile, so it adds here. Because of that, what we get is CH2 plus here, and this bond has been used to make a new bond. Since the electron is lost from this carbon, we get a positive charge. The similar reaction is possible with H plus also. this bond attacks here, and what we get is you can see here when we add H plus to alkene, what we get is a carbocation. So this is a method to generate carbocation. Already we have seen when we add H plus to alcohol, we get carbocation. Similarly, when you add H plus to alkene, we get carbocation. And the reaction involves a nucleophilic attack to H plus. Generally, we don't call this as acid-base reaction, even though it is taking H plus. The reason is this cation will further add with the negative part of this to give a compound. So both H and the negative part both are adding to the double bond. So that's why we call it either hydrobromination or hydrochlorination, hydroiodination, like that. We don't call it as acid base. Now let us go to the second category of electrophile, that is carbon attached with more electronegative atom like oxygen, nitrogen and halogen through single bond, double bond and triple bond. First let us go for the single bond. Because of the more electronegativity of oxygen or nitrogen and halogen, there is some del plus on carbon and del minus on the more electronegative atom. The electronegativity increases like this. So the del plus on carbon also increases. So the del plus on nitrogen is less compared to oxygen, which is less than this. Even though there is del plus, it is not sufficient enough to be attacked by nucleophile. That means even though there is del plus in the amine, the nucleophile cannot attack this because it is not sufficient. When you go for oxygen, like this, in this case also there is del plus, but this is not sufficient to be attacked by nucleophile. So the reaction won't take place. But there is a type of compound, that is aziridine. So aziridine, it is 3-membered ring. In this case, not only del plus on this carbon or this one, but also there is ring strain. So the molecule tries to remove the ring strain by undergoing some chemical reaction. So this may be opened up by a nucleophile. So this can attack here, it can be opened up. So what we get is NH minus nucleophile. The attack, it is trans. So it will attack from the back side of the amine. Further, if I attach an electron withdrawing group to this nitrogen, then the same reaction will be more facile because the electron withdrawing group pulls the lone pair of electron. As a result, the electron density on nitrogen decreases, so it tries to pull the electron from this. So the del plus on this increases, so it can be easily attacked by nucleophile. Similarly, we have another functional group called epoxide. So because of this more electronegative oxygen atom, there is del plus on this carbon. So it can be attacked by a nucleophile. Suppose if the ring size is 5, like this. Now, will the nucleophile attack here and open up this ring? No. So the reaction will not take place. So here 3-member ring, there will be more ring strain. But in this case there is no ring strain, so the reaction will not take place. So this reaction, it is not only because of the electron withdrawing character of nitrogen, but also it is because of the ring strain. In this case, if you add some acid, then the lone pair of electron will attack here and we get positive charge on this. Because of this positive charge, the reaction will be more facile. Even a weaker nucleophile like alcohol or amine or even halogen can attack this. So now I have increased the electrophilicity of this carbon by adding H+. Not only H+, there are so many Lewis acids known to increase the electrophilicity of this carbon. Maybe scandium, titanium, vanadium. All the transition metals are known to bind to this lone pair of electron and increase the electrophilicity. If I go for an epoxide like this, the earlier one it was symmetrical, but this one it is not symmetrical. If I add nucleophile with minus charge, whether it will attack this carbon or this carbon. Because of this oxygen atom, there is del plus on this as well as this, which will be attacked by the nucleophile. If it is aliphatic epoxide, generally the nucleophile prefers to attack the terminal carbon. The reason is the steric hindrance is very less here compared to this. Because of this group, there will be some steric hindrance at this carbon. So the terminal carbon is attacked by the nucleophile. At the same time, if it is styrene oxide like this, so it is not aliphatic, now it is aromatic ring. In that case, the nucleophile prefers to attack the benzylic position. So what we get is if you add Lewis acid and methanol, what we get is further this hydrogen will be taken up by this minus. So what we get is this product. What is the reason why the benzylic position is attacked by the nucleophile? Why not terminal? There is steric hindrance here, but when you go for terminal there is no steric hindrance, but still the benzylic position is more preferred. Why? Because the del plus on this is more compared to this. Because of this benzylic ring, the del plus is more on this carbon. And the benzylic cation, whatever we get, that is more stabilized, resonance stabilized. So that is the reason why we get the nucleophilic attack on this benzylic carbon. Now let us go to the halogens. The electronegativity is more for fluorine and less for iodine. But iodine is easily displaced by nucleophile than the fluorine. Even though the del plus is more on this carbon compared to this is readily displaced than this one. The reason the minus charge can be accommodated in the d orbital of iodine, and also since the size of iodine is big, it can easily accommodate the minus charge. But in the case of fluorine, it will be small, it cannot accommodate 2 more electrons. Because of that, the leaving group tendency is more for iodine. So it increases like this. But the electronegativity is increasing in this order. Now, when this is attacked by nucleophile, there is del plus, so it is attacked by the nucleophile. The attack is from back side, so what we get is this type of reaction is called SN2 reaction. The nucleophile attacks the carbon and substitute the bromine atom, halogen atom. So nucleophilic substitution. What about if the nucleophile is within the molecule? For example, I go for this. So in this, the minus charge, that is the nucleophile, is within the molecule. So it is in the second position of the halogen. You may know, because of this electronegativity of bromine atom, we have positive charge here. In order to fulfill that, this will fall. During that time, the valency increases, so the Br gets eliminated, and what we get is an alkene. So this reaction is called elimination. You can say E1Cb elimination. So this elimination proceeds through carbanion. So we call it carbanion, and the mechanism is E1. Suppose if it is one carbon away from this, that is minus charge and leaving group, what we get is a ring, a cyclopropane ring. If the number of carbon it is 2 or 3, then also we will get the corresponding cyclized product. So it may be cyclobutane, pentane, goes like that. Not only carbanion or alkoxide or negatively charged species, even alcohol can attack the halogens to give the corresponding nucleophilic addition product. This Br minus takes this H plus, so what we get is this also possible, but this reaction generally goes through carbocation. So the Br will get eliminated to form carbocation, and that will be attacked by weaker nucleophile like alcohol to give the product. So this is what we call SN1 mechanism. So this SN1 mechanism is more preferred when these 3 groups are alkyl. Tertiary carbocation is more stable, so that will be formed, that will be attacked by alcohol. Like the earlier case, if it is like this, then if you add base to this, what we get is O minus, that will attack to give epoxide. So epoxide also can be formed through this, not only cyclopropene or butane. Similarly, aziridine. The mechanism is same. The lone pair displaces this. Now, let's go to this category. In this, carbon is attached to more electronegative atom through double bonds. So this function group, it is known as imine, and this is carbonyl. So what will be the reaction? Now the minus charge, that is carbanion, can attack here. So when it is attacked, the number of bonds on this carbon increases to 5. So what happens? This bond goes over nitrogen and we get minus charge there. So we get this. So minus charge is used to make bond between this carbon and this carbon. So that is this one. And this bond migrates over nitrogen. Further, this may take proton. It will become NH. This reaction is known as Mannich reaction. Imine is formed because of the more electronegativity of nitrogen atom. There is del plus on carbon that is attacked by carbanion. That is called Mannich reaction. Not only this carbanion, even alcohol can attack this. So what happens? When this attacks there, again what we get is O like this. So the minus will take this H plus. So what we get is this one. If two heteroatoms were present on the same carbon via a single bond, and one of the heteroatom contains hydrogen, then it will eliminate. That is not stable. That will eliminate to give the product. So that is, now this is unstable because two heteroatoms are attached to that same carbon via a single bond and one atom contains hydrogen. So what happens? This comes back, eliminates. So what we get is so this is a reversible reaction. Instead of that, if I add aromatic ring, the nucleophilicity of this aromatic ring is somewhat less. So I go for this indole. Because of the resonance, the nucleophilicity on this carbon is very high. This can attack imine. Further, it is same. What we get is like this. This hydrogen is taken by that, falls here, we get the managed product. So carbanion can add to imine, that is called managed reaction. Alcohol also can add, but the reaction is reversible because the product whatever we get, that is unstable. I will explain about this in some other compounds also. Last one, this is aromatic ring, that also can attack imine. The carbonyl group may be aldehyde or ketone, ester, acid chloride, amide and anhydride. So with carbonyl group, there are several functional groups. Now, how the nucleophile adds to this? In the case of aldehyde and ketone, it is same. The nucleophile, for example, C minus attacks here, then we get O minus. If you put R, that is ketone. So reaction pattern will be same for aldehyde as well as ketone. But the case of ester, acid chloride, anhydride. This OET, chlorine and this acetate can act as leaving group. When the nucleophile, that is carbanion, attacks here, so this step will be same. So what we get is O minus, this carbanion, OET. But this minus charge can come back and can eliminate alcohol to give a ketone. Similarly, in this case, HCl will get eliminated. In this case, acetic acid will get eliminated. Not only carbanion, even OH minus, this also can attack here. So the mechanism is same. When it comes back, this is getting eliminated. So what we get is acid. So this is called acid hydrolysis of ester. Base catalyzed hydrolysis of ester. Similarly, if you add amine, that also will displace this, but it requires somewhat high temperature. Compared to ester, acid chlorides are more reactive. You can see that very clearly. Because of this more electronegative atom, the del plus on this carbon is higher compared to the ester. So because of that, even if you add water, the water will attack this because the del plus is more on this carbon compared to ester. On the other hand, ester is more stable in the presence of water. It is weak nucleophile. So what we get is acid. What about amide? So this carbon, it has del plus. There is no doubt about that because of the oxygen atom and the nitrogen atom, sorry, this minus, there is del plus on this. But what happens? This del plus is somewhat satisfied by this lone pair of electron. That is, the lone pair of electron involves in resonance to exist like this. So now you can see basically it is iminium ion with O. Because of that, the del plus on this carbon is not as much as expected. It is somewhat less than the expected. So generally OH minus can attack here. The same mechanism we can write. And can come back to give acid. But this reaction will not take place at low temperature. On the other hand, ester hydrolysis can take place even at 0 degrees C if you use lithium hydroxide. But for this reaction, you need to give some heat energy because the electrophilicity on this carbon has been satisfied by nitrogen lone pair. Now, I go for some more nucleophile, that is CH2 minus. Now, I go for some more carbanion and I try to attack the aldehyde using that carbanion. Look at this carbanion, it is from nitromethane. So this can attack here to give the corresponding product. So this reaction is called Henry reaction. Other word, nitroaldol. So basically it is similar to aldol reaction, but instead of aldehyde we have nitro group. So we call it nitroaldol. If this attacks the aldehyde, then this is aldol condensation. So this is aldol product. What about this carbanion generated from active methylene compounds? This also will attack. It will give you the corresponding product. So this is called Knoevenagel reaction. You check the spelling, it is wrong. This is the first step in the Knoevenagel reaction. Further, it gets decomposed, eliminates water to give alpha beta unsaturated acid. But this is the first step. The carbanion attacks the aldehyde to give the corresponding addition product. What about this? This is from ethyl acetate. So this carbanion also can attack aldehyde, and what we get is like this. So this also is possible. Another one, I have taken nitrate. So this is acetonitrate. In that I have generated carbanion. This also can attack aldehyde to give the corresponding addition product. So the reaction, so the mechanism is same. Only we change the substituent here. We get different product. I can go for one more. That is CH3MgBr. So this minus attacks here to give this product. This is nothing but very well known Grignard reaction. What about the addition of alcohol or weak nucleophile to aldehyde, that is carbonyl group? Is it possible to add alcohol to this carbonyl group? No. As such, the nucleophilicity of this oxygen is very less. It cannot add here. But if I add some catalyst like H plus, then the reaction will proceed. I explained that the carbonyl group, that is lone pair of electron, that is nucleophile. So that can attack H plus. What we get is, since the lone pair of electron is lost, we get a positive charge on oxygen. Now the del plus on this has been increased to great extent. Even water or methanol can attack here. So this attacks, and what we get is like this. But the reaction won't stop here. Since the reaction is carried out in H plus, further this lone pair of electron can add to H plus. So again we get oxonium ion. Now this lone pair will fall, and what we get is like this. Further, this can be attacked by alcohol. Now let us go to the amine nucleophile to give this acetal protection. So amine has a lone pair of electron. So basically, this is can attack protection. The carbocation added to OH to give the corresponding. All the mechanism, all the steps involves the basic concepts of electrophile and nucleophile. Since there is plus charge, the Cl minus or X minus or some counter ion of this carbocation will take this, and what we get is the product. Important reaction of amine is with carbonyl group. In carbonyl group, there is del plus on this carbon. So the lone pair of electron can attack here and can go like this. For example, I take R, here some X. So what I get is R, the lone pair of electron has been lost. So what we get is O minus X and R. This X may be hydrogen. So the functional group, it is aldehyde. It may be alkyl or aryl. So it may be ketone. It may be halogen like Cl or Br. Cl is the most common. So acid chloride, or it may be acetate. So that is acetic anhydride, or it may be OET. So it is ester. So now, since there is plus charge, this O minus takes that proton, and what we get is NH, COH, X and R. Now, if you look at this, there are two heteroatoms. One is nitrogen, another one oxygen. Both as hydrogen atom. So in such case, what will happen? Even if one hydrogen is present, then it will eliminate water. So the lone pair of electron from nitrogen will fall here, and this will act as leaving group. So what we get is R, NH, double bond, C, X and R. Since the lone pair of electron is lost, we get positive charge. Now this bond may fall, and what we get is R, N, C, X and R. This is the pathway when X is equal to H or alkyl. So that is, in the case of aldehyde and ketone, what we get is imine. So this functionality is known as imine. If the X is halogens or acetate or alkoxy, so that is the functional group. If it is acid chloride or acetic anhydride or ester, then the pathway will be something different. That is, instead of water, this group will get eliminated. So what we get is HX. So we may get HCl or acetic acid or ethanol. So the product, whatever we get, will be amide. There are several functional groups based on nitrogen. First one, it is aniline. It may be simple alkyl amine. It may be hydrazine or hydroxylamine, phenylhydrazine, semicarbazide. There are so many functional groups based on nitrogen. All this nitrogen can behave in the same manner. So you will get imine with all these compounds. The case of hydrazine, both the nitrogens are same, so there is no problem. But when you go for hydroxylamine, nitrogen has one lone pair of electron and oxygen has two lone pairs of electron. Which one will attack the electrophile? Is it nitrogen or oxygen? Generally, the nitrogen is more nucleophilic than oxygen. The reason is oxygen is more electronegative and it pulls the electron density towards it. As a result, the electron density to attack the electrophile is very less. So this will not act as nucleophile. So only nitrogen will attack and what we get is oxide. So for example, if you take aldehyde and if you treat with hydroxylamine, what we get is oxide. So this OH may be towards this side or this one. So they are E or Z isomers, so diastereomers basically. Is there any possibility to convert this oxygen to act as nucleophile, not nitrogen? Yes, it is possible. If you attach electron withdrawing group to nitrogen, then the oxygen will serve as nucleophile. For example, I go for the very well-known reaction N-hydroxyphthalimide. So I have attached two electron withdrawing group to this nitrogen. Now, if you add base, the base will abstract this proton, will get O minus. Then if you add methyl iodide or some alkyl halide, then this will attack here. So what we get is so in our case it is CH3. So not amine, even though there is lone pair of electron, this lone pair of electron involves in delocalization. So because of that, the electron density is very less on this nitrogen. What about this phenylhydrazine? There are two nitrogens, but they are not same. In this case, I can explain the nucleophilicity based on resonance. The lone pair of electron on this nitrogen involves in resonance. As a result, the electron density here it is very less compared to this one. So there is more del minus on this compared to this. So this nitrogen will act as nucleophile. Similarly, in the semicarbazide, this lone pair of electron involves in resonance, but this one is fully available to act as nucleophile. So this nitrogen is nucleophilic than the other one. What about the double bond? Addition to aldehyde. Is it possible? So this is nucleophilic and this position is electrophilic. Will it attack? Yes. It attacks here to give, I write like this. So since the bond is lost on this carbon, we get positive charge and here minus charge. Even though I have written like this, basically it follows a 6-member transition state. This reaction is known as Ene reaction. Basically it proceeds through a 6-member transition state. So this attacks here and we get a positive charge. The minus charge takes this proton and this bond falls here. So basically it is a concerted mechanism. So it will come under pericyclic reaction since it proceeds through a cyclic transition state and it is concerted mechanism. Even the aromatic ring like phenol, which has more electron density compared to benzene, it can attack formaldehyde. So what we get is hydroxymethylation. Now let's go to the triple bond as well as in para. That is only, so we will get a mixture. Nitrile. Because of nitrogen, there is del plus on carbon and del minus on nitrogen. Now, if you add OH minus, this will attack. What we get is so it will take proton and what we end up with is, so basically it is imine. After addition of base to the nitrate, what we get is imine. If you further water or base will add here and what we end up with is OH. On this carbon atom, there are 3 heteroatoms, all 3 as hydrogen. So that is highly unstable. What it will do, this bond will fall here and it will eliminate ammonia to give acid. So this is hydrolysis of nitrile using base. What about carbon nucleophile? Is it possible to attack? Yes. I go for a name reaction called Thorpe nitrile condensation. So the carbon ion generated from this can attack to give like this. So further, since it is imine, it can be hydrolyzed to give ketone. What about weak nucleophile like water? As such, water cannot attack this because the nucleophilicity of water is very less. So it cannot attack this. Now, let us go to the alpha beta unsaturated system. For example, I take cyclohexanone. In this, because of the more electronegative oxygen atom, there is positive charge on this carbon. So there is del plus on this carbon. In order to satisfy that charge, so it is similar to allylic cation. So this bond migrates here, and what we get is del plus. Now there is positive charge on this carbon. So in nucleophile, whatever we add, it can attack here as well as here. If it attacks here, what we get is so the bond migrates over oxygen, so we get this one. So nucleophile adds to this carbon and the counter ion will add here. So the nucleophile and the counter ion are in 1,2 atoms. So 1,2. So it is called as 1,2 addition. If the nucleophile adds here, the nucleophile will be here and the counter ion will be on this. Say for example some metal. Now they are on 1,4 atoms. It is called as 1,4 addition. Generally, strong nucleophile prefers this one, 1,2 addition. Weak nucleophile prefers 1,4 addition. For example, CH3MgBr, it is very strong. Since the carbon ion is there, that is very strong, it will prefer 1,2 addition. On the other hand, if you prepare dimethyl lithium cuprate, Gilman's reagent, that prefers 1,4 addition. So not only this carbon nucleophile, even amine or alcohol or even the anion generated from active methylene compounds, they are somewhat weak. So they prefer 1,4 addition. Enolate. All these nucleophiles, they are somewhat resonance stabilized and the reactivity is somewhat less. So they prefer 1,4 addition. So this 1,4 addition is called as Michael addition. So in order to predict the mechanism, it is very important to find out the electrophilic and nucleophilic center in the molecule. Let us go to the most common functional groups and let us try to predict which atom is electrophilic and which atom is nucleophilic. The most common one, it is alkene. Since there is double bond, so this is nucleophile. Similarly, if you go for alkyne, because of this multiple bond, this acts as nucleophile. If you go for alcohol, the oxygen has lone pair of electron, so this is nucleophilic. At the same time, because of the more electronegativity of oxygen atom, the electron density from this bond is pulled towards oxygen. So we get del plus on this carbon as well as this hydrogen. So this hydrogen can be taken by a base. So there is nucleophile as well as electrophile. I go for ether. There is lone pair of electron on oxygen. So this atom, it is nucleophilic. Because of this oxygen atom, we have del plus on this carbon. So that is electrophile. So we have both nucleophile as well as electrophile. So electrophilicity may be less to be attacked by some nucleophile, but there is some del plus. What about aldehyde? On oxygen atom, there is lone pair of electron, so this is nucleophile. Because of the more electronegativity of oxygen atom, there is del plus on carbon, so this is electrophile. Similarly, in the case of ketone, oxygen is nucleophile and carbon atom is electrophile. So you can try this for acid chloride or ester or acetate. What about amide? Amide is something different from the earlier case because it has lone pair of electron which involves in resonance. Because of that, it exists like this. So the del plus on this carbon is somewhat less than expected because of the resonance. Now the minus charge is on oxygen and plus charge on nitrogen. This lone pair of electron cannot act as nucleophile. Amide nitrogen cannot act as nucleophile. The reason is it involved in resonance. As a result, it gets positive charge. So this is nucleophilic position, and this is somewhat electrophilic because again it is more electronegative atom. So this is electrophilic but still less than expected or predicted. What about this hydrogen? Because of this positive charge, the electron cloud from this is pulled towards nitrogen. So there is some del plus on this hydrogen as well as this. So if you add a strong base, then this hydrogen can be abstracted by that. If you add butyllithium or LDA, this hydrogen may be taken because there is some del plus on this hydrogen. What about thiol? Because of the lone pair of electron, this is nucleophilic. Similar to alcohol, there is del plus on this hydrogen as well as on this carbon. The next one, it is amine. There is lone pair of electron. This can attack the electrophile. So this is nucleophilic. Because of the more electronegative atom, there is little del plus. Because the difference in electronegativity between this and this is very less compared to oxygen atom. So only 0.5 difference is there. So because of that, there is very small amount of del plus. So that is not sufficient to be attacked by even strong nucleophile. So even CH3 minus cannot attack this. Let's go to the aromatic system. As such, this is nucleophile because there is double bond. When I add electron donating group to this, then this position, these two positions becomes nucleophilic. Electron donating group prefers ortho and para product. So these two positions becomes nucleophilic and we get the corresponding addition product. When I add electron withdrawing group, then this position becomes nucleophilic, that is meta position. Now the question is, what are the groups will direct to the ortho and para position and what are the groups will direct to the meta position? Generally, our students memorize the groups, but it is easy to understand. Let us consider system like this, if there is a lone pair of electron, maybe 1 or 2, even 3, then this particular portion is equivalent to, now this can involve in resonance. So the electron from the group is going into the double bond. So it is increasing the electron density on this carbon. So this is ortho position here. Simply you can remember like this. If the atom attached to the aromatic ring contains a lone pair of electron, then that is ortho para directing. For example, if oxygen is attached to this, maybe phenol or ether, acetate, NH2, acetanilide, thiophenol, thioether, halogens. All these atoms have lone pair of electron, and the lone pair of electron can involve in resonance and can increase the electron density on the ortho and para position. So they are ortho and para directing. What about beta directing group? If there is del plus on this atom, then this is equivalent to this system. So this pulls the electron from there. So the double bond can involve in resonance to induce positive charge on this carbon. That is nothing but this carbon. So such system can decrease the electron density in the ortho and para position. As a result, the electrophilic substitution takes place at the meta position. What are the groups? First one, it is aldehyde and it may be ketone. If carbonyl group is attached to this, because of more electronegativity of this oxygen atom, there will be del plus. So that is del plus. Because of that, goes here. It is similar to alpha beta unsaturated system if you consider this portion alone. It may be even ester or amide. Addition to that, we have also nitrile group. Because of this more electronegative atom, there is del plus here. One more group, it is nitro. Because of the positive charge on this atom, the electron will be pulled from the ring. Even a system like this, this is the salt formed between aniline and HCl or some other counter ion like HSO4 minus. Here there is plus charge on this atom. Because of that, the electron density from the aromatic ring is pulled. Another system, it is CF3. Here, because of this fluorine atom, there is del plus on this carbon. So because of that, the electron density can be removed from the aromatic ring. Similarly, we can go for sulfone or sulfoxide In this case, even though there is a lone pair of electron, because of this double bond and more electronegative atom, it prefers to pull the electron from here. Instead of giving the electron, it prefers to pull the electron. So it is something different from whatever I mentioned. It has a lone pair of electron, but instead of donating that electron, it prefers to pull the electron density from the aromatic ring. So basically it is meta-directing. Similarly, we have sulfone. There is no lone pair of electron and there is del plus. Because of that, it results in meta-directing. Easily you can remember like this. If the aromatic ring, if it is attached to a double bond like this, and in the double bond, this is more electronegative than A, then that will lead to meta-directing. There are few exceptions, that is CF3 and NH3 plus. In this there is no double bond. Because of the more electronegativity or because of positive charge on this carbon, it directs to meta position. The last video we discussed about the nucleophilic position and electrophilic position in a molecule. In that, we have come across lone pair of electron, multiple bonds, alpha beta unsaturated system, like that. What about the first category, that is positively and negatively charged species? Do they exist in the molecule as such? No. Positively charged as well as negatively charged species, they are highly reactive. They will not exist in the molecule as such. We have to generate them and we have to react them with another molecule. First, let us go to negative charge. I go for carbanion. This carbanion or other negatively charged species, they are mainly prepared by abstracting the hydrogen. On the atom, there will be some del plus. Because of the del plus, the electron density or the bond pair electron is pulled towards this. Because of that, we will get del plus on hydrogen and a base can abstract this. So we get carbanion. I explain like this. Consider this aldehyde. Because of the more electronegativity of oxygen atom, there is del minus on oxygen, del plus on this carbon atom. Because of the del plus, the electron is pulled towards this carbon. So we get del plus on this. Further, because of this, we get del plus on this also. So compared to this carbon, it will be less on hydrogen. But still, there is some del plus. If you use a strong base, like OH minus, then this can be taken. So what we get is further, this can involve in resonance to give the enolate. I can explain like this also. This aldehyde exists in enol form and this proton is highly acidic now because of this oxygen atom. So there is del minus and del plus on this. So this hydrogen is taken by the base I can explain in this way also. For the same reason, this hydrogen can be taken by a base to give the corresponding carbanion. So if there is electron withdrawing group like nitro, nitrile, ester, aldehyde, ketone, then the alpha carbon is somewhat acidic that can be taken by a base to get the corresponding carbanion. We can also get carbanion from alkyl halide. For example, I go for bromomethane. If I add magnesium, then what I get is methyl magnesium bromide. So this is nothing but Grignard reagent. The magnesium gets inserted between this and it undergoes oxidation. Now it is in magnesium 2 plus, here it is magnesium 0. Basically it is oxidative addition, but during that time the oxidative addition, the word oxidative addition was not that much popular. So after the discovery of palladium catalyzed reaction, we started to use that. In this, the CH3 has minus charge and metal has plus charge. Not only this compound, if there is any carbon and metal bond or oxygen or metal bond, nitrogen or metal bond, then the metal has positive charge and the carbon has minus charge. Carbon, oxygen and nitrogen, they have minus charge. Similarly, you can go for lithiation. Methyl lithium, there is positive charge on lithium and minus charge on carbon. We have also phenyl magnesium bromide. In this, phenyl has minus charge and magnesium has plus charge. Not only these two, we have also one more method, that is through decarboxylation. When the carboxylic acid is treated with some base and when you heat that, it can undergo decarboxylation. Initially we get the salt, then it can undergo decarboxylation to give minus charge, carbanion. Similarly, you can go for O minus and N minus also. First, let us take acid. This acid dissociates in solution to give minus acetate and H plus. So there is minus charge on this oxygen. But the nucleophilicity of this oxygen is very less since it involves in resonance. So this is resonance stabilized. If you add a base, even a weak base like sodium bicarbonate can take this to give the corresponding sodium acetate. Since it is metal, it gets plus charge, oxygen, it gets minus charge. What about alcohol? Because of the more electronegative oxygen atom, the electron density is pulled towards that and we get del plus on this hydrogen. Now base can take this to give hydroxide. Generally we add sodium hydrate or sodium hydroxide. So you will get sodium ethoxide or sodium ethoxide, potassium tertiary butoxide, all are known. The same way, even this phenolic proton can be taken by a base. What we get is sodium phenoxide. What about N minus? Is it possible to generate minus charge on nitrogen? Yes, it is possible. The most common one is diisopropylamine, NN diisopropylamine. Because of this nitrogen atom, which is more electronegative, there is del plus on this hydrogen. That can be taken by a base. It should be strong base. Sodium hydroxide cannot take this proton because the electronegativity of an atom is somewhat less than oxygen. So we need a stronger base like butyllithium, which can abstract this to give this lithium salt. So this is called LDA, lithium diisopropyl amide. Similarly, we have LiHMDS or KHMDS, hexamethyl disillyl amide. The structure will be like this. Here, whether it is lithium or potassium. Based on that, we call it lithium hexamethyl. There are 6 methyl groups. So hexamethyl disillyl, 2 silicon atom, amide, N minus, it is amide. Hexamethyl disillyl amide. So it is generated by the same reaction. The hydrogen will be taken by a base like butyllithium to give the product. What about carbocation? How do we generate them? Already we have come across that one. First one, to alcohol, if you add H plus, the lone pair of electron on alcohol will attack that, and what we get is, now this bond can fall on this to give carbocation. This is more favored, the formation of carbocation is more favored if all these groups were alkyl or aryl. That is, tertiary alcohol can result in the carbocation easily than secondary or primary. The reason is tertiary carbocation is more stable. Because of that, it is formed. Second one, if you add H plus to alkene, then this attacks here, and what we get is this carbocation. So this is the second method. When you go for symmetrical alkene, there is no problem. But if I go for an alkene like this, styrene. Now the question is whether H plus will add here or here. It is very simple. The most stable carbocation will form in the addition. If H plus adds here, what I get is this secondary carbocation. If H plus adds here, then I will get carbocation here. That is this is primary carbocation. Since secondary carbocation is more stable than the primary, this will be the major product. This will be attacked by the counter ion. For example, take Br. So Br will add here. So that is called Markovnikov addition. The third method to generate carbocation is from alkyl halide. Alkyl halide in polar solvent dissociates to give carbocation and X minus. This is another method to generate carbocation. So this is called SN1 reaction. Again, if it is tertiary alkyl halide, then the formation of carbocation will be more facile. Unlike carbanion, the carbocation whatever we have generated, it can undergo three types of reaction. First one, it is nucleophilic substitution. Second one, it is elimination. Third one, rearrangement. In the case of carbanion, it is not like that. The whatever carbanion you have generated, it has to attack the electrophile. That's all. But here, there are three possibilities. First one, nucleophilic substitution. That is the regular one. The carbocation, whatever we have, that will be attacked by nucleophile to give the product. This is the simplest reaction. The other pathway, it is elimination. I go like this. The carbocation, it has a positive charge. There is deficiency in electron density. To fulfill that, this bond may fall here to give an olefin. So this reaction is called as elimination. E1. It is called elimination because before that it was generated from this compound. I have eliminated HBr to get this product. From this you cannot say it is elimination, but from the starting material, if you compare the starting material and the product, we have eliminated HBr. Next one, it is rearrangement. Let us consider this product. This undergo dissociation to give carbocation like this. Now, whatever I have got is primary carbocation. If it undergoes rearrangement, then I can get tertiary carbocation. That is, if I shift this hydrogen here, then what I get is the H minus migrates here along with this electron. So because of that, I get positive charge here. So this is called rearrangement. Basically, it is one to shift of this hydrogen atom. And what we get is a tertiary carbocation. That is the driving force for this reaction. And this type of rearrangement is known as Wagner-Meerwin rearrangement.